Yeah, so I'm the founder of Radican. We got started in Redwood City about 3 years ago. I'm coming out of the Stanford design program, which is actually within the mechanical engineering department. I don't have a background in it, but I discovered it kind of in grad school in 2007 and got very passionate about building products that have an impact. So I think you'll see there's kind of a theme in some of the things we work on. We got started with the premise that hardware startups kind of face some challenges and need some things that software startups don't need. Software startups kind of have a yellow brick road in Silicon Valley. There's someone to hold your hand every step of the way. You can get started with a laptop and a Wi-Fi connection, basically, what anybody has in their dorm or at Starbucks. But hardware is a little bit different. So we started around a shared workspace. We still have that. That's in Redwood City. And we've just actually relocated our staff product development consulting office to Soma in San Francisco. So hopefully this is the first 2 steps in continuing to grow. So yeah, we offer a bunch of services under one roof. Most of what we work on are smart products. It's very rare that you build a product that only rests in one discipline. Usually you want to get different types of designers, like industrial designers and product designers, UI, UX design involved. You need mechanical engineers, electrical engineers, you need manufacturing expertise. Your average startup founder, especially if they're new to hardware, doesn't have all this expertise. One person's never going to have all that expertise. So we try to bring all those resources together under one roof. And as I mentioned, yeah, our mission is supporting hardware startups. So 100% of our clients right now are hardware startups, and we've worked with over 30 in our 3 years of business. So of those 30 startups, and this is only what's been made public so far, so these numbers are definitely higher behind the scenes, and it just hasn't been made publicly available. We've raised collectively $7.6 million through crowdfunding campaigns like Indiegogo and Kickstarter, basically, and almost $55 million through private and venture funding on top of that. So you might recognize some of these names. These are all startups who we've had some critical role in their product development in the formative stages. And here are some of the companies who work or have worked out of our space in Redwood City. I know it's a lot of logos, but maybe you see something you recognize. We're very fortunate to have some excellent sponsors, so some really big corporations who want to help startups, so we're able to give access to companies that we work with in our incubator program, like SolidWorks licenses, Altium designer seats that are kind of out of reach. You know, these things can cost $5,000 a seat, so it can be tough if you're an entrepreneur just starting out to make that kind of a purchase. And we also have a wide network of partners, people who we can refer our clients to, who do things like scaling up for manufacturer, like Berkeley Sourcing Group, things that we don't do. It helps us to have those partners in place. So with that, our process is very heavily focused on prototyping, so building physical things and iterating very, very quickly. Well, prototype is always kind of going to be something experimental. So this is actually one of the first prototype vertical takeoff and landing aircraft. It was designed by the French Air Force. We don't hear a lot about the French Air Force. This might be why. So probably not many of us in this room would be thrilled to get into this aircraft, right? I mean, it doesn't really look like it's going to have straight level flight at any point during its trajectory. But there's always this experimental aspect, right? And there were many, many things like this that were tried until something worked, right? So now these things exist because we tried a lot of stuff along the way that didn't exactly work and we learned, right? So now there are vertical takeoff and landing aircraft that people would happily get into. The process from the outside often looks chaotic and very messy when you're running through a lot of iterations very quickly. If you're an engineer and you have a workbench at home or something like that, you probably know what I mean. It makes perfect sense to you, but from the outside, it looks like a bomb has dropped. But there really is a strategy behind it, and there's kind of a method to how we're moving through these projects. And I think it's that strategy that's the single most valuable thing that we provide, you know, way beyond access to machines and all that. So we really use prototypes with a purpose in mind, and those purposes are to challenge assumptions first and foremost. So if you sit down and you have let's say a planning meeting for 2 hours, and you plan where you think the market is heading, and you think what some opportunities might be and what you think people might be interested in, You could have a great plan, but it's still based on a lot of assumptions that are hard-boiled into there. And you haven't really made any progress on testing whether or not those assumptions are good and bad. A prototype can help you challenge those assumptions head on. So you think something is a good idea, you try it, and you get that feedback immediately. It's a really effective tool for communicating. So I'm going to do a thought experiment later, but if you try to explain to somebody what you're working on in text, it can be really hard. You know, hit somebody with a wall of text explaining what your product does, it's not very compelling. If you put a prototype on the table, you can say a lot. We have a saying, a prototype is worth 1,000 meetings. So it's also a really compelling tool to raise funding. VCs and other investors, there's kind of been this, like, for many, many years, this is definitely changing now, but this aversion to hardware because it requires capital up front, because people don't really understand if the technology needs development, are they going to be able to do it or not? These are really hard things to determine, but if you put a prototype down on the table that's working, same is true for crowdfunding, then it appears as though, even if there are still some challenges to resolve, it appears that you've resolved a lot of them, and it also shows that your team is capable of doing it, right? You've gotten this far, you can probably get the rest of the way. So it's a very compelling tool. That's part of communication also. It's a really good tool for discovery. You don't usually think of it that way. You think of, like, I'm just implementing something that I thought of and it's going to come out exactly how I thought it would. But that almost never happens. So you're actually, as you build, building is kind of a thinking process too. It's a physical thinking process. And so you can discover new opportunities, especially when you hand somebody a prototype and they interpret it differently than how you intended. That can create some opportunities. And in the same vein, it's a very powerful tool for getting feedback, honest feedback, meaningful feedback, and validation that you're on the right track or that maybe you need to. Here's an example of a very first small prototype. Believe it or not, this is a solid-state machine that turns sunlight directly into sound, which is a form of mechanical work. And this was part of a project to try to design an open-source solar electric generator so that anyone anywhere in the world without access to a clean room or cadmium or photovoltaic cells could extract electricity from the sun. So here's a kind of first validation test with some Home Depot level hardware and a Fresnel lens from a science classroom. We ended up recreating this at about a 10x scale. So there's about a kilowatt of solar energy going into this. This is what's known as a thermoacoustic resonator. That's the kind of magic. But anyway, this is entirely hand-built, all from materials that can be sourced anywhere all over the world. Interesting set of constraints, but just to give you a sense of, when I say hardware, you probably weren't expecting something like that, right? We've worked on deep-sea marine equipment. There's a big problem in the fishing industry. The overarching problem is sustainability. And one of the main elements of that is what's called bycatch, which is you throw down a net, you trawl around, you pull up the net, and there's a lot of stuff in that net that you didn't want to catch, juveniles or endangered species that are illegal for you to catch. You can pull up enough in fines in 1 year, in one net to close down a fishery for a year. And this is stupid. I mean, we're depleting the oceans, and a lot of it's just being thrown back overboard because you can't sell it. One statistic is Louisiana Bay shrimp fishermen have 42 pounds of bycatch for every 1 pound of shrimp that they can sell. And that's basically, dead and dying in the net being thrown back overboard. So it's a big problem. We're trying to design a smart net that only catches the right type of fish. And we're starting by trying to put sensors and intelligence into the net itself. It's a very challenging environment to work with, big temperature fluctuations, enormous pressures, salt water is highly corrosive, barnacles and stuff like that. And so this is what the device ended up looking like. That's now in sea trials in the Pacific Northwest. But it started out, this is our prototype pressure vessel in a bucket from Home Depot. We're looking at probably less than $100 worth of equipment here to start testing out what are the light levels you need underwater in complete darkness, how does the cloudiness of water affect your view, and also some pretty basic questions about heat transmission through the acrylic, because we're using very powerful LEDs that are pumping out tremendous amounts of heat. So these are all questions you can start answering very, very simply and cheaply and quickly before you get to creating a custom pressure vessel that costs many thousands of dollars and a fully functional system that's going down for trials. In the same light, we worked with the Scully motorcycle helmet. It's a super futuristic motorcycle helmet with a heads-up display like Google Glass. And they came to us with the question of basically what is the range of adjustability that's needed so that the optical stack is in the appropriate field of view and at the appropriate focus for anybody who could put this helmet on. And the basic architecture of the helmet's being used for every size of head, right, for everybody. So we needed to first kind of figure out how we were going to answer that question. And while there's some very high-tech optical stuff going on here too, there's some really very simple, basic things. And we started with this test rig. One question was, well, okay, there's no X or Y axis on my head. There's no origin. If you try to compare my head to somebody else, it's a very complex three-dimensional shape, right? An organic shape that has essentially infinite variation. So we first created the solution of a coordinate system by locking your head into a plywood board in three-dimensional space. So here you see now there's an X and Y axis on my head because I'm actually locked in with a very powerful magnet to this plywood board. So anybody of any height, of any head size, we can lock them in and they'll be in the same place in physical space. And we can start to take these measurements, which we did by having the optics components on the end of a chopstick and asking people, okay, what's the highest up you can see, what's the farthest down you can see, and all that, right? So very simple, very quick, and this is all in the first week of working on this project, we're answering these very basic questions of not just the content, but even designing ways of how we're going to learn that information that we need to know. Scully's now in manufacture, so you should see those early version helmets coming out. As far as like a lean development process, this is kind of the core question that you should be asking at all times. You want information, right? That's really what you're after, is some data. And the question is, what is the minimum amount that you can do to get the data that you need right now, as quickly as possible, right? As efficiently as possible. It's not always immediately clear what data you're looking for, so there's kind of an ambiguity part to there. I would say if you work in a big corporation, a lot of R&D product development happens behind closed doors. They might do focus groups, but you basically don't get feedback on if what you're doing has value or not until this thing is sitting on a shelf and you see whether or not people buy it. So that's a very expensive failure. We try to accelerate this into what I call kind of the virtuous cycle, which is just an iterative cycle of building prototypes, testing them in realistic scenarios, and then learning from that and integrating it into the next step. And really, I view everything from the napkin sketch to the manufacture as just an iterating through a process very similar to this, with just increasing constraints as you go along. But I will come back to that. Yeah, this is very similar to what in the software world they call Scrum, which is you try to have a deliverable on the order of like a week or 2 weeks at the most. If you're working on a prototype that takes you much, much longer than that, you could have been doing smaller things and learning things along the way. So really the faster you can move through that, the better. We call them prototype sprints. A sprint can last a half a day, it can last a day, a week, or yeah, at the longest 2 weeks. So what I mean by a rapid prototype is it's also pretty straightforward. It's just evaluating a concept with the minimum investment of time and other resources. And because you're not making that huge investment, like cutting a tool for injection molding, you're not really financially invested in staying the course, right? So this is early on when you can still be prepared to change direction. If a test doesn't exactly go the way you thought, you need to be flexible. So what this allows you to do, basically, if you do head down the wrong path, it's cheap because you learn that very quickly and you can course correct, which means you're nimble. And it also means that that data is coming back to you every day or every week or however quickly you're iterating. So you can be guaranteed that you're making progress on your product during that time. A rapid prototype is not your final product, so it doesn't need to be subject to all of the constraints that your final product does. It's really about understanding what are we building for, what are we trying to test with this, and that determines the constraints that apply to it. And so with that, there's this kind of idea of preserving ambiguity. It's okay if not all the details are worked out in every prototype. Certain things can kind of be left for the next one or left open to imagination, or even left open to the next version after the first version of the product that you launch. It's very rare that you get to launch your first product with 100% of the feature set that you thought you would when you started designing. So here's an example of a rapid prototype. This was a project I did in grad school years ago, actually for Audi. Their Q7 is the largest car they make. The user manual for it is 3 volumes, each over 100 pages. nobody ever reads it. So they came to us with the prompt of redesign something to replace the user manual. So we came up with this idea of what if you had a looking glass and you could kind of just browse around your car, and if you wanted to know what something was, you could press the question button and it would overlay the information over that, and then you could get that information right away. So here we are testing this in a car. It's not an Audi, but it is a car, so that's pretty good. It's what we had available to us at the time. And this is, as you can probably see, some Play-Doh and some saran wrap and like probably literally 0 cents worth of materials. So can anybody see, though, what is maybe wrong with this approach? It's evident from looking at this prototype.
You might lose that. You lose whatever.
Okay, yeah, sure, you could lose it. It's also pretty dangerous if you happen to be driving down the highway and you wonder how to use your cruise control. The last thing you want people doing is waving around their cabin with a magnifying glass looking for where that thing could be, right? And that was something that wasn't really obvious when we were building it. It seemed like a great idea, right? It seemed like this could be a cool answer, but as soon as you get there and you test this object that has no functionality, you actually learn something very concrete about the product. So here's another example. This is actually from the same prototype sprint. We built a bunch of different options in about 10 minutes, and we were trying to figure out easier ways, less distracting ways of like navigating through menus, right? Inputting stuff if you need to interact with the user interface. So we thought about putting a trackball on the steering wheel. So can anybody see some problems with this particular implementation?
Well, if you turn the wheel, you can't get control.
Exactly. The whole point of a trackball is that it's a coordinate system. It's the X and Y. You can input left and right and up and down, and you always know if you move it left, it's going to be left, or if you move it up and down. But the moment you turn that wheel, you no longer have a fixed coordinate frame. It becomes a very confusing user interface question. Does it move with the wheel? Does it stay put? Right? So yeah, and you, again, this is a paper plate and a foam ball, and it took 5 minutes, so it's fine to have that failure and learn that, but you start to understand the constraints of the environment you're working in, what opportunities are interesting and which are not, and from a very, very minimal investment. I suppose this is open to debate, but I think fundamentally your most valuable resource is time. If you legitimately do have a good idea, there's a lot of good ideas out there, specifically in this particular area, and somebody else is going to have that idea or an idea a lot like it if they haven't already. Basically, every good product has competition. That's kind of just a fact of a free market. So if you want to accomplish something that other people haven't done yet, you have to do it quickly because it's going to happen. And we know, all of us know, that time is the one thing that is definitely finitely limited for everybody. So with that, it can be fun if you're a technical person to sit down and kind of tinker and, you know, write another little function that does something that might be cool. But I would say that's just tinkering. It's not necessarily prototyping because it lacks purpose. So you should always understand why it is that you're building a prototype, even if what you end up learning from it isn't what you set out to learn. So it's specifically to answer questions, or we said like to address challenges that you like. If you think something is risky, if you think something about your product might not work, start with that. Don't save that for last. Start with that. And lastly, it's a really powerful tool for learning and gaining insights about your product that you don't even know yet, and really nobody knows about yet if you're working on a new product. And so that means that if you're going to get that feedback that you didn't expect, you need to be open to receiving it. A lot of people go out and they kind of survey like, hey, wouldn't it be cool if you had this, you know, something that waters your dog or something? And 7 out of 10 people said, yeah, cool. That's not really a useful insight that helps you develop that product any further. As I mentioned, it's a powerful tool for communicating ideas, so I want you all to do a thought experiment with me. This is an actual email that I received from a teammate of mine working on the same project that we saw earlier. So I want you to kind of visualize in your mind, let's say you're the engineer, it's your job to implement this thing. Picture in your mind what this looks like, what this would be like, and what she's trying to describe. It seems pretty like thorough and specific, right? It seems like you should be able to figure out from that. So does everybody kind of have a picture in their head of what this thing would look like? So is that what you pictured? How many people pictured that? 2.5 people. So my point is you probably had some relatively different idea in your mind. But now as soon as we put this in front of you, which again is some masking tape and some saran wrap, it becomes a really simple conversation to say, like, here's what I'm trying to communicate. It looks like this, it works like this, and we can sit down in the car and we can actually kind of play around with it and we can learn something from it. I'm showing you a lot of like really, really early phase stuff further into future phases of the product when you're actually getting to manufacture and nailing things down. But as a general guidelines on how to prototype effectively, one is you keep it as rough as you can to get the information you need. So as you get closer to manufacture, it's getting more refined, but you don't want to over-invest if you don't need to, right? It's not smart to cut a tool for injection molding on the first design you ever make of something. So you want to keep it as rough as you can. And I'll build on a little more detail on all of these. Is also use as much third-party hardware in the beginning as you possibly can. It's like standing on the shoulders of giants, right? You don't need to design and like program a PIC from scratch if you can just be using an Arduino. And lastly, when you're testing or when you're showing these things, it can actually really help to show multiple different directions or multiple variations. And I'll kind of give you a little bit of the logic. This is actually coming from some research results, some academic research results from my group. So first of all, if you have a rough prototype, it inspires better conversations because people are immediately aware that I'm not coming to you with a final product. I'm not asking for your feedback on the fit and finish and the choice of materials, right? I'm trying to get you to kind of imagine along with me what this thing could be like. And it becomes a little bit more playful and a little more interactive. Somebody is also not going to be terribly scared of breaking this or using it the wrong way or anything like that, right? So it kind of invites that interaction and inspires those conversations that are more generative than critical, which is usually helpful in the beginning. So as far as leveraging existing technology, there's some Arduinos right there. Very simple platform. This is a prototype of a social tracker that can track when you're having a social interaction with another person. And the idea was that this was going to be used at Ferrari, for they have teams of hundreds, if not thousands, of engineers collaborating on a single vehicle. And the aim of the research project was to show that the physical interfaces in the engine, where one component plugs into the other, actually mirrors the social network map of people interacting on the engineering team. So that was the premise, but leveraging all stuff that already existed. As far as showing multiple variations, if I just show you one thing, it's easy to get critical. It's easy to focus on, like, if you don't feel great about this object that I'm presenting to you, you start trying to unpack, like, what's wrong with it, right? How could we change this? But if I show you multiple variations, there's this exact opposite effect. You kind of like, your mind gravitates to the aspects you like of each one, right? And it becomes more positive. And then you get this effect where then there's like a second generation. It's almost like a sexual reproduction kind of thing, right? Where you take all the best aspects of the previous generation and you roll them into the second generation, which you could do because this is a lot like what you might call A/B testing for banner ads, right? You put up two different banner ads and you see which one gets more clicks and you use one that's more like that. But you can do the same thing in hardware, right? And it kind of takes the conversation in that more positive direction. Somebody will probably get mad at you at some point for making a mess or noise or for disassembling the kitchen sink. But sometimes this is all needed, in the spirit of progress. And so this is just a kind of idea that I affectionately call the prototype uncertainty principle. If you are actually building something new, then you don't know exactly how it's going to turn out at the end. Nobody does. I don't know. Greg Fisher doesn't know. You don't know. So you need to, that's that theme of preserving ambiguity. But it's the things that come out of that ambiguity. It's the things that you tried that didn't work that you learned from, or the kind of happy accidents along the way. Well, like I showed it to him and he thought it was this, which is really interesting because I didn't tell him it was that, but that's how he interpreted it, and that tells me something about him and his relationship with this product. Let me know if I'm going over on time, Greg. I am going over on time. Okay. Anybody can leave at any time. So we have just a couple different types of prototypes, we try to distill it down to the most simple aspect. We call that like a critical function. So what must it absolutely do? I like this story. This is a good example of building many variations. This is a subset. I think there was over 20 variants. These are all prototypes intended to do the same thing. Any guesses on what that might be, what the critical function is here?
Fire spitball.
Okay, that's pretty good. That's a good guess.
It's a lighter.
A lighter, okay, yeah, a lighter, gas pump, gun, all kinds of. So this is actually supposed to be a hanging feature for the end of a welding torch. So when you're welding, the tip of the torch gets very hot. Anytime you change materials or thicknesses, you need to go back to your welder and adjust settings, so you need to put it down. Some students of mine went to test this idea with some welders, and what they learned from that was welders work on construction sites and in giant concrete shops with steel tables where you can put a welding torch down wherever you damn well please. It doesn't matter. This is not a problem that they have, but they learned that very, very early on. And it got them to sympathize with what the actual problem was, and they ended up making a remote control that builds into the handle of the welding mask, which you always have in one hand, so that you can adjust your settings remotely, whatever welding machine you're using. So it was testing this one thing, they learned they were wrong, and they got the insight that got them on the right path. So I think if you talk to a lot of startup founders, by the way, including successful startup founders, they will tell you the business is not exactly turned out precisely how they envisioned it when they started out. It's a lot about this kind of reacting to what's out there. Sometimes it's much more about the experience that a user has than it is about the actual functionality. So for example, if you're building a shower, so this is the Nebbia shower that you may recognize from Kickstarter on the right. And this is actually a bunch of hardware store parts that creates the same experience, more or less, if you close your eyes under the shower. So this was what they had first, and we actually jumped in with them and kind of did a sprint to get to something that looked more like the final product in about 2 months. So if you see, that's what was actually featured on Kickstarter, the prototypes that we built together. And at the same time, obviously, it's motivated a lot by industrial design. That's part of the experience, part of like how you respond to this product. People are calling the shower like a smart shower, even though there's no electronics in it. Well, why is that? It's because it like fits into a smart lifestyle, right? It like looks good next to your iPhone or something like that. It's part of. So how it looks like is also part of the prototyping process, like what materials, how it feels in your hand. And we'll often break that out into 2 separate types, what we call a looks like prototype. So here's one that's had a form designed, right? It's been 3D printed. This is a relatively simple thing. It doesn't do anything. And then here's the actual engineering functional works like prototype. That's the same product as what I just showed you. These are intended to be the same product, ultimately, but not yet, right? So we're testing these individual aspects in isolation first. So I had in here just some examples of different processes and what they cost, because we promised that would be in the talk, but I can kind of gloss over that a little bit. Maybe you guys can, if you have questions, we can come back to this. This is doing some custom casting of expanding urethane foams for some parts for the Scully helmet, and you can see they're custom 3D printed molds, so these are one-off casting. And then if you want to get a little higher, this is like a 5 to 25 run silicone mold. So you print a positive, cast the silicone mold, and then cast the positive back in that mold. Some sheet metal parts. This is something that's really, really cheap in volume. I think a funny anecdote about these 2 parts is they cost, for the 2 of them, was $500, and for 12 of them would have been $500. So you kind of get that like immediate fall off in scale with certain things. Sheet metal is one of those things. And obviously, as you scale up past the level of your prototyping and building stuff yourself, you need to actually start sourcing components at a larger scale, handing off aspects of that process. So that's somebody like Greg Fisher. The process is really about introducing constraints over time, incrementally, one at a time, preferably, so that you're gradually refining toward a product through this iterative process. And I wanted to show you I'll end on this one. But I thought this was a really great, yeah, so these are some funky looking scissors, right? Have you ever had that problem where you're cutting through something like a big piece of cardboard and you get like 2 really great cuts in and then it just like sucks after that?
Yeah.
So this pair of scissors is intended to design that exact, solve that exact problem, right? And here it actually shows you pretty concretely how we moved from literally prototyping in cardboard, drawing stuff out, trying it out, through multiple different 3D printed variations, moving toward functional machine blades, and then finally towards something that's starting to look like a pre-production model. And this all happened in the span of a few months. So yeah, just the virtuous cycle. I think I can stop there. Yeah, thank you.